Another interesting case when we have multi-CPU systems and threading support at the user and the kernel level is related to synchronization. Consider the following situation. We have one user-level thread T1 running on top of one kernel-level thread on one CPU, and this thread currently has a mutex. A number of user-level threads may be blocked, but then on another CPU, currently a user-level thread T4 is scheduled. Let's say this thread T4 actually needs to log the same mutex that's currently held by T1. Now, the normal behavior would be to place T4 in that case on the queue that's associated with this mutex. That's what we saw during our earlier discussion about threads and concurrency. However, on a multi-CPU system, it's possible to have this situation. The owner of the mutex, the one that's currently executing the critical section, is running on one CPU. And when we request that same mutex from the other CPU, it is possible that by the time we take this thread T4 and context switch it and place it on the queue that's associated with this mutex, in that amount of cycles, maybe the critical section here is very short and T1 will actually complete its execution. If that is the case, if the critical section is short, then we're better off if the thread that needs the mutex actually just ends up spinning on the CPU, just burning a few cycles, waiting a little bit until T1 actually releases the mutex. If it takes less time for T1 to release the mutex, we're better off spinning than actually taking a thread, context switching it, and queuing it up on a mutex queue. So for short critical sections, don't block, spin. For long critical sections, we will have the default behavior where a thread is actually properly blocked, placed on a queue that's associated with a mutex until the mutex is freed. We call these kinds of mutexes, which sometimes result in the thread to spin and other times it results in the thread to block, adaptive mutexes. Clearly, these only make sense on multi-CPU systems since whether or not we spin is going to depend on whether the owner of the mutex, like in this case, is actually running on the other CPU. In a single CPU system, that definitely won't be the case, so then it doesn't make sense to consider the use of adaptive mutexes. Early on, when we first introduced mutexes, we said that it is useful to maintain some information about the owner of the mutex. These adaptive mutexes are one example of how such information can be useful. When we try to lock a mutex, if the mutex is currently busy, we can look quickly who the owner of the mutex is and then verify whether that other thread is running on another CPU. That will tell us whether or not we should spin or block. Clearly, we'll also need to have some idea about the kinds of critical sections that are used with this mutex so as to determine whether it's likely that the owner of the mutex will release it quickly so we can spin or not, and in that case, we need to block. And at the end, I want to make some final points about destroying threads. Once a thread is no longer needed, so once it actually exits, it should be destroyed and its data structure, stack, etc. should be freed. However, since thread creation takes some time, like data structures need to be created and initialized, it makes sense to reuse these data structures, essentially as if we're reusing the actual threads. The way this is done is when a thread exits, it's not immediately destroyed. The data structures are not immediately freed. Instead, the thread is marked as it's on a death row. And periodically, a special Reaper thread will perform garbage collection, which means that it will actually go ahead and free up all of the data structures that are associated with the threads on the death row. If a request for a thread comes in before the thread has been properly destroyed from the death row, then its data structure and stack can be reused, and this will lead to performance gains since we don't have to wait for all the allocations.